All right, cool. So thank you for all for coming. I'm Camilo Payan. This talk is going to be very demo heavy. We're going to be going back and forth between the slides and these. So first things first, probably not, but can everyone read this?
Yeah.
Just so-so? Yeah, we can, cost me nothing. I can always jack up the, the font size. All right. So you can find me on Twitter, cpayan with an underscore, or actually you would be able to find that at camilopayan.com as well. So, all right, let's get started. Git is a version control system. So its job is to keep and track a history of all the changes that you make to files in your code repository. So just for a little bit of audience participation, how many of you use Git every day already? Right, yeah, same here. And how many of you are using something else? How many of you are using nothing at all to keep track of your changes?
I've been using SVN.
Right, yeah.
Version? Okay. Soft version of it.
We were talking before about like CVS, SVN, and I used to use SourceSafe, which was very confusing. But Git is definitely one of the most popular ones thanks to github.com at this point, in large part, and also the Linux kernel. But the big question with this and this whole talk is that we're going to be going behind the scenes in Git and creating our own Git repository from scratch. We're going to use Git init. We'll make our own commits and things like that from scratch and make our own history. But what's the point of that? What brought you here today? I know a lot of people would say curiosity. Personally, I'm not my personality, I'm not a very curious person. If something works, I'm totally fine with that. It works. But the fact is that when it comes to Git especially, it breaks. There's a pretty good XKCD comic for exactly this. A lot of the times you start out your first job and they just tell you, memorize these shell commands, and if it ever breaks, just delete everything and re-download it. But that's not exactly it's not a satisfying answer, even if it does get you out of the gate quickly. What you need to have to be able to fix your Git repository when it goes wrong is a good mental model of how it works. And in this kind of work, having a good mental model of how things work is essential. If you're working in PHP, having a good mental model of how PHP executes using different processes is going to save you tons of time because you realize you can hand wave a lot of memory management things and things like that. Same with database work. Especially if you're using an ORM, it's good to know how your database is working behind the scenes. So that's really the main impetus behind understanding how Git is working behind the scenes, at least to me. For a little bit of history, Git was initially a toolkit for a versioning system instead of the versioning system itself. So because of that, there are two kinds of commands in Git. There's the porcelain commands that are for day-to-day use. Can anybody tell me, just yell out any kind of porcelain commands that they've probably used already? Right, exactly. Everything that you use day-to-day, those are porcelain commands. They're meant for you to be used by people. But then there's also plumbing commands, and these are commands that do low-level work, and they're meant to be called from scripts or piped together, and that's the kind of command that we're going to be using today. So let's start our demo. Right now I have a totally empty directory, so we'll just start a Git repository in here. And as you can see, it tells you that it creates a new Git repository in .git hidden folder. And let's take a look inside of .git. You might have already configured a couple things in your Git repository. You might have configured your user email or your user your name. Would probably be useful information to configure, as well as remotes. Any remote servers or whatever go into that config file. But today we're going to be working with the objects directory, the refs directory, the index file, which is not here yet, but I promise you it's going to show up, and this head file right here. So let's get right into it. So we're going to start out with blobs. Also, this is a very Pokemon heavy talk because I need to make it fun for myself while I write it. So the first things first is going to be a blob, here signified by a ditto. And we're going to create our very first file. Let's add a little content to it. Just add a little word ditto. Should that be bigger? If y'all can't read it, just let me know. And we're going to use our very first plumbing command. and this is git hash object. The -w is to make sure it gets written to your Git repo, and we're going to give it the file that we want to hash. So the value that we get back is the key. Git is a content addressable file system behind the scenes. It's a key value store. So what happens is the contents of our file get hashed, and then that gets stored into the .git folder, and this becomes the key that we use. Just to prove that, so Git uses a SHA-1 hashing algorithm. Ooh, there goes my HDMI. It's finicky. Please come back. Huh.
That's my tech word too. Please. Please work. You're supposed to work.
Oh, buddy.
That's odd.
Yeah, I've got just, and I have the big screen just wrong. Nah, it's just the cable. All right, I think it's coming back.
Yep.
All right, and it didn't disconnect. Cool. So we did this hash object. So Git uses the SHA-1 hashing algorithm. Hashing algorithm, for those that might not know, is a math function that takes the data of arbitrary size and hashes it down, gives you a result of the same size every single time. I can't remember what the actual size of SHA-1 hashes are. But the important part about this is that no matter what input you put into it, you're always going to get the same output with the same input. It's deterministic that way. Right, as long as you use the same exact data, you'll get the same exact result, which means we can kind of prove that by using it directly, by using SHA-1 via OpenSSL. And you can see that this isn't just the stuff that we have in the file. It also has a little bit of metadata. It tells Git that it's a blob. It tells it the length of the file, 6, which includes this little null character right here. But we get the exact same hash back in the end. And let's go ahead and find out where it ended up. This is inside of our Git folder. In the objects folder, we have that hash being used as a, where's my mouse? As the file that we just saved. So you can kind of see that it also gets split up. B9, and then the rest of the file name is 7A47 and so on. It splits that up because on some file systems there are limits to the number of files that you can have in a directory, and apparently 2 characters is all you really need for that to stop being a problem. And let's go ahead and use another plumbing command. Actually, let me make my life a little easier. First, we're going to take a look at what's actually there. Run cat on that. It's gibberish. So the content of our file got compressed when it got stored into our Git repository. And this is what it looks like when we just try and output it. But obviously it's unreadable. But Git has a command for that. And that command is cat file. -p in this case is for pretty printing. And we'll give it the hash, without any separation or anything like that, the hash that we got. And we get the contents of our file back. So you can already kind of see how Git works. It's going to use these hashes, which if you've had to work with your Git commits, you know there's a lot of hashes involved. But all that stuff is stored in the back end. Let's go ahead and change our file now. And we'll add another Pokemon to it. That's a joke that's going to pay off in a second. And let's run hash object on that again. Now, as we remember, as long as the inputs are the same, we're going to have the same result when we run it through our hashing algorithm. But now the input isn't the same. It's a different file, different hash. And let's take a look at that using cat file, our plumbing command. And we have ditto and sudo-wudo in there. So that was actually really surprising to me because I always figured that Git or any version control system was going to keep the differences between each change. But in this case, we can see it actually snapshots the whole file every single time and stores it in your Git repository. And let's go ahead and keep adding stuff to our. Does anybody know the lyrics to the song? Yeah.
Whoa.
All right. And let's go ahead and make a hash object for that too. So, all right, let's run find and take a look in our objects directory again. We can see all of these are being stored as files in the back end of our Git repository. We have all these blobs, we have objects, things are really rolling, we have a real repository going on. But can anybody tell me, like, it kind of makes sense, if this gets pushed up to GitHub or whatever and you slurp it down again using git pull, fine, all the content is there. But what is really missing from this before it even makes sense to a person? I can give you a clue here. What's the big difference between these two folders? These names actually make sense, Pokemon.txt, lyrics.txt, but those names are useless. No one's going to want to talk about B97A47. So we really need file names. And for file names, we're going to need trees. Pseudo-wudo. Told you that would pay off. So Git stores file information using trees and blobs. File contents go into blobs, file names go in trees, and trees also tie several files together. And you want to tie several files together because that's naturally how a commit is going to work as well in the long run. Long run from our perspective, doing everything piece by piece. So let's create our very first tree. Doesn't seem right. Nope, I skipped a slide. Yoink. First things first, I promised you an index file, and this is a plumbing command that creates it, git update index, and we're going to tell it which file we want to add to our index. So if we take a look in our Git repo, here it is, the index file that I was promising you. What's in it? More gibberish. But you can already see a little bit. So this was, again, compressed, zipped up, but our file name is actually there, invisible. And let's run git status, pretty regular porcelain command. So can anybody tell me which command we went through very slowly over the course of like 5-7 minutes?
Git add.
Right. Took a long time to get here, but we created the blob, put it in our Git repo, and then added it to our staging area. And that tells you that the index itself is the staging area. That's what that file is. And fun fact, we can also add files that don't even exist anymore, because even though if we take a look at Pokemon.txt, it's Ditto and Pseudo-wudo, we actually have the information from when it was just Ditto still in our Git repository. So by using the hash that we already had, we can use a much more complicated update index. And a lot of it is still familiar. We have add here. We have the file name that we want to give it. But now we have this hash. We have the file permissions. And we tell it, instead of looking at the actual file itself, Pokemon.txt, we use cache info here to tell it, look inside the Git repository for this hash instead. And if we run that and run git status, you can see Pokemon.txt was added to our staging area, but it also still recognizes that there's changes between what's in the file system and what was added. Because Git's smart like that. For now, let's go ahead and write our tree with another plumbing command. And what did we get back? Another hash. It's hashes all the way down. And if we run find again, everything is stored here. These first 3 lines are all blobs that we created for Pokemon.txt. Here's the B9, so on and so forth. But we actually just created this one, D999, so on and so forth. And that is the tree that we just created. So everything gets stored back here. And if we take a look, using cat file again, at what our tree object looks like, it's basically a list. Actually, a list that looks a lot like the information that we gave it about this, the file permissions, the hash, and the file name. what do we have here? We have the file permissions, the hash, file name, and also a little bit of extra data to tell it what kind of object we're looking at, a blob in this case. The other thing that trees can do is act as an equivalent to directories. So, if we make a directory, and we'll call it dragons, and let's create another Pokemon.txt file. As we know, everybody comfortable with folders knows you can have files that are the same name, but in different directories, this file system won't get confused. And neither will Git. We use git update index and add that to our staging area. Run write tree again, different content, new hash. And let's take a look at what's in this hash. All right, we have the same content that we had before. The blobs, their names, the blob, their name, but now we have a tree inside of our existing tree with its own hash. And this one is just called dragons, which was the name of our directory. And if we take a look at that hash, we have another list, and here we have the blob that's associated with it. So all this stuff gets created. We keep on building one on top of the other. One hash goes into the other, and in that way, everything gets tied together. If we take a look at our staging area, everything kind of looks the way that we expect it to. We have this Pokemon.txt file, the old version with just Ditto in it, and the lyrics.txt file. So what would be the next step before we can really call this a Git repository? We've staged everything, but right now we have to commit it, you know? So that will be, does anybody know which Pokemon this is? Because I had to look it up. I thought keys were evocative, but it's called a clef key, apparently. So now that we have things in our staging area, we can build our commits and then also create our commit history, which is going to be the next important part of this. Knowing full well that every time that we create stuff or use hash object or write tree, we're creating more and more objects. So it's getting more and more bloated. That's why you don't want to, well, not really bloated. Everything there has a purpose. But here we go. Now we're going to create our first commit. Up until now, the plumbing command that we've been using is write tree. Now we're going to use another one called commit tree. In this case, the tree that we've been working with just now. If you're real good, you can recognize the hash from earlier. And we'll give it a simple commit message, first commit. And let's take a look at what is in this. Cool. So this is what Git looks at when you give it a commit hash. Tells you, this email address doesn't work anymore, but it kind of saves the things that you would expect: the author, the committer, your commit message, but also a reference to a tree object. So you have tree and the hash that goes with it. So up until now, the other thing, well, it'll be a giveaway. Up until now, you probably noticed I've just been copy pasting stuff from my notes. That makes it real easy. And the reason for that is that as long as you have the same inputs, you're always going to have the same output. So as long as I have the same information in the files, I'm always going to be using the same hashes. I can't do that anymore. I can't do that at this point at all. Can anybody tell me why? It's because of these little guys that were here. This is the time, yeah. And the first time I gave this talk was in 2017. That information is not going to work anymore. Though I guess I could mess with the clock and really get my timing down. So yeah, now that it's different content, I'm going to have different hashes every time that I make a commit. Now let's update our tree with the latest Pokemon.txt information. Also, let's take a look at git status. It doesn't know that we committed it. We just created a commit, and that's sitting around in our objects folder right here. If I remember right, it started with a 5. But Git itself is not aware that any of this happened. It just knows that it's there now. So now if we update our index, yeah, that's not it. It's a cool iTerm2 feature that is currently getting in the way. We'll update index and give it the latest Pokemon.txt. That's ditto and sudo wudo. Let's just run right tree again. We have another. I can copy paste this one because it's information that I already had. And let's create another commit. We'll give it the commit message second commit. And if we take a look at that one, it's actually going to give us broadly the same thing with different timestamps and a different tree. So now this tree is the new tree that we created with the Pokemon.txt file all updated, 9C, so on, and the current timestamp. And let's, oh my god. Take a look. We'll use git log on this second commit. And we can see as a commit history, we just have second commit. It doesn't know about the first commit that we created. And similarly, if we go all the way up to that first commit and run that through git log, again, it is just the first commit. It doesn't know about the second commit. So, and of course, if we look at our actual git status, it doesn't know about any of the commits. It still thinks all these things are in the staging area. Because they are. They're all still in the index file. So what we need to do if you wanted to create an actual commit history is go ahead and create a commit that doesn't just know about which tree we're using, but also knows which commit comes before it. So in that case, I'm going to do a little bit of copy pasting. And then a little more copy pasting. So here we have, we're going to give it the message second commit. We're going to run commit tree, our plumbing command again, with the tree with everything in it, including ditto and sudo wudo. But the addition here is adding -p for parent or previous, depending on what you want, with the hash of the first commit. If we run that, we get yet another hash because its hash is all the way down. And let's take a look at that now, and it's changed. Obviously, the time has changed because it's been a minute or two since we created that commit. But now, not only does it know which tree it was looking at, it also has a new line for parent, and that has the first commit that we created. Now, if we run git log using the commit that we just created, all right, now we're cooking with gas. We have an actual commit history. It understands, what was committed when based on the trees, and even knows how much was changed. So to recap all of that we've been building on, our blobs contain the contents of a file. Those are snapshotted and hashed and put in our Git repository with the hashes acting as keys. Then these blobs can be put together into trees. Trees can be combined with other trees to make our directory structure, as well as blobs to make sure that those file names are connected to each blob. And then commits are built from trees and can reference each other to make your commit history. So everything kind of flows in that way. And now let's run git log all on its own. No hash. We got nothing. No commits. It even says fatal because apparently it's that serious. But nothing has come up yet. So what makes that work? That's going to be references. Last time I did this, I did a Who's That Pokemon thing, but I don't know if this is the right crowd for that.
I don't know this one.
It's a Rotom crossed with a Pokedex, apparently, which is a thing that happened in the cartoon sometime in the last couple of years. But yeah, so we're going to be using references. References make this work, and they're stored in the refs folder, which is one of the folders that I said that we'd be looking at, along with objects, which obviously, let's take a look at our objects folder. It's getting pretty long. But if we take a look at refs, it's actually empty. -r. But it does have two folders inside it, tags and heads. Tags you might have used git tag to deploy things. That's basically all I use them for. And heads is what's going to be the most interesting thing here. So let's find our last commit hash. Where are you, buddy? All right. It's this one. And we'll go ahead and echo that information into a file in our refs heads folder. We'll call that poke. So now if we run git log, we can give it that more human readable name, and it knows. It knows exactly what we're looking at. So looking at the contents of, there's nothing in there except for this, this hash that we gave it, the commit hash that we created. And there's a safer git way to do this as well. So you can use git update ref, and then again, refs heads. We'll use master in this case and give it that same information. Now that we've updated that ref, if we run git log right now, it also knows. So these files that are really just hashes behind the scenes, a small file with just the hash information inside refs heads, those end up becoming your branches. So if you wanted to, you can go ahead and check out poke, and it'll know about that. Now, oh, I really need to fix these notes. I jumped ahead and then backwards. But let's take a look at what is in our head file, because this is what tells you exactly which branch you're on at any given time. Right now, since we just checked out poke, you can see it marks it as a ref, and it tells it exactly which file to go to. It's just the file name at the end of the day. Real simple. And of course, if we check out master and do the same thing, that's how it always knows which branch you're on at any given time. It's just that one file inside of your Git repo. Let's get let's get this whole commit hash, if I can find my cursor. And let's check out that hash for that commit. So this is, you might have seen this before if you were messing with rebase or anything like that, but this is what's called a detached head state. So if we take a look at our head file, now instead of the nice, neat file name that we had before, we just have the hash, and Git will complain because it's not attached to any reference in the refs folder. However, I mean, there's nothing really to be worried about, as you know now. It's just the hash there. You could actually go in and change it yourself to something else if you would like. It tends to happen a lot with rebases gone wrong. Now, so yeah, we stepped through every single part of this. We created a Git repository that contained our data, that was able to tie everything together into directories, then tie it together into commits, and then tie those commits together. Everything is still there, including, not that one, including a bunch of stuff that we aren't even using anymore. Somewhere in there is that second commit that we created that's not attached to anything. I don't remember the hash, obviously, but it's there. That's my phone ringing. But yeah, armed with this kind of knowledge, you can also kind of conceptualize at least how other things are going to work as well. I originally had an example of rebasing here, but that was really complicated. But one thing that surprised me when I first started using it was, when I first started using Git, was I kind of assumed cherry pick would, I mean, I guess literally, when you think of the metaphor, nothing happens to the cherry when you pick it, you know? But when you do use cherry pick in Git, what happened, the way that command works is it takes a commit from one branch and you can put it on the end of another branch, is a general idea. But that creates a new commit, which I didn't get. You know, to my mind, with like a basic CS education, I was thinking, well, it's a linked list, it probably just changed the pointer, why would it have to change anything else? But now you can kind of tell, actually, you know, everything changes. So if we kind of go through it, it takes the commit that you're cherry picking, it takes the tree hash from that commit because it doesn't need anything else from that commit information. Everything else is just going to get written again. The new thing that's going to happen is it's going to change the parent, and it's going to change the time, because if you're already changing the parent, I mean, now just for consistency's sake, you need to change the times as well. The video call dropped again.
Okay,
Yep, which is a shame because that's like the second to last slide.
I'm still seeing it
Yeah, okay.
for now.
And then it creates a new commit with that tree hash and the current head commit as the parent, and that creates a new commit. And rebase probably follows a similar line of thought, but every time I tried to explain it, I got really confused. So that has been the whole talk. We created a whole, you know, kind of Git repository from scratch at that point. I wanted to acknowledge a couple things. Scott Chacon wrote a really good book called Pro Git. It goes into basically everything you can do with Git, and then the latter chapters are this. And then I wanted to do this talk because I saw a very similar talk. I mean, it's basically the same talk by Emily Gia going through these same steps. But she can't be everywhere at once, so I'm doing this talk. Thank you very much for your time. I really appreciate it.
Very good.
And